Thinking back, a lot of what we looked at in the first chapter and even the second chapter was about linear functions and linear terms. Then in our last section there, we spent a lot of time on quadratics, so natural place to keep going from that point is to talk about more general things in terms of nice natural number powers of x, where the most broad description for such things is the term polynomial, where polynomial comes from the Greek poly for many and Latin nomen meaning name. So this is to say that we have many names, many terms in a polynomial. And technically speaking, anything that we did with linear terms, those could be thought of as polynomials. If there was only one thing in there, it'd be what's called a monomial. If there were two, it's called a binomial. If there were three, it's called a trinomial. And usually anything more than three, we just call it a polynomial. But the broadest way we can define something like this is for constants that are non-zero, an minus 1, all the way down to a1 and a0. We have that f of x is an x to the n, all the way down to a2x squared plus a1x plus a0. It's a little bit small there, but it's hard to fit that exact definition into place, where if you want to think about things that are or are not polynomials, it's stuff like this, where that 3x to the fifth plus root x squared plus 5 is what we would call a polynomial of degree 5. The degree of a polynomial is the largest power n of x. That one is 5. So that would be degree 5, whereas something like negative 3x to the 6th minus 3x to the 5th plus 18x to the 4th, that would have degree 6 because x to the 6th is the largest thing in there. And notice when we're talking about the values for the a's, the coefficients, those can be absolutely anything we want them to be. The main thing is we have to have natural number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on as our powers of x. So things like rational or root functions, those don't work as would negative exponents. So if you have something like a negative 3x to the negative 2 or an x to the 1/2 power, those aren't our natural numbers, so we don't include them. Where, to understand why we keep going here beyond just saying, hey, this is math, we have some math, let's do more math, and sure, for mathematicians, that is itself a convincing enough explanation, but some of you might become mathematicians, but most of you probably aren't that interested to begin with, so let's try and get a little bit more motivation. That when we're talking about something linear, if we think of it in terms of behavior, slope, overall change, it doesn't do a whole lot. It starts in one way, goes up in a nice clean block, and keeps going up in that same linear pattern forever and ever and ever. Things like the amount of money you make at a job before you get a raise, I suppose, where you're just getting that same amount forever and ever until you lose interest in the job and you quit, or you get that raise, or your boss fires you. It's always going to follow that same fixed pattern. It doesn't change in any meaningful way, except for, if you want to think about it, that consistent rate of change itself. But we talked about how that's not really good enough in a lot of cases to describe things. There's a lot of stuff that's not linear. So we have things that are maybe more quadratic for talking about a thing that comes up maybe a little bit and then comes back down. But you have that sloping value until it hits a peak, and then it slides, where something like, say, the value of Dogecoin before and after Elon Musk happened to talk about it on Saturday Night Live.
I keep telling you, it's a cryptocurrency you can trade for conventional money.
Oh, so it's a hustle.
Yeah, it's a hustle.
Why didn't you say that, man? Don't fall to everybody. It's a hustle.
To the moon!
That's almost a quadratic pattern there around that peak. But even then, those aren't all the possibilities we could want. Those aren't all the possibilities we could hope to use. For another example, we could think about something like the effects of human disturbance on the nesting pattern of birds. In this case, what I found was nesting patterns of Spanish house sparrows, where if we try and describe that using trend lines, a linear description there, hopefully you can see, isn't very useful for anything other than maybe a couple values. And while a quadratic description, it gets a chunk of the pattern, it certainly seems like it catches that peak decently well, it looks like it might keep coming back up afterwards for some reason that we might not understand. There might actually be some relationship there that more people means more food for the birds and therefore better nesting. So it might have a second peak later that you can't capture with a quadratic, but you can do that a lot better with something cubic, something with an x cubed, a degree 3 polynomial, where, to be sure, this is an example of linear and nonlinear correlation, which is a bit heavy into stats, sort of thing that most of you probably wouldn't have seen, even if you took that in high school, even if you took it here at college, you might not have seen very much with that. So it's a little bit outside the scope of our class, but I think it does help get the point here that when we're talking about things with functions, we're trying to model certain relationships. And some relationships have more complex behaviors over time than one constant unchanging rate, or a rate that changes at some point, goes up and it comes back down. There might be more curve, there might be more going on there, and that's why we get into these more general things with polynomials. Where the next thing we're going to talk about then is a lot on how we can handle graphing, general polynomial functions.